Good morning, everybody, or good afternoon. I'm here to talk about some of the work that we've done from Carnegie Mellon about a different way of doing dynamic simulations that actually uses an event-driven approach rather than using time steps to simulate to progress through time. And we use this by doing quasi-steady state simulations using PowerFlow. So just as an outline, really, I'll talk about our quasi-steady state framework and some of the motivation behind it. Then I'll talk about how we progress through simulation in rather than time steps, we actually go through in events. And this is inspired from circuit simulation, which have used similar techniques. Then we'll talk about backtracking algorithm, and then finally show some results. So just a general motivation, really there are two main forms of simulation analysis done in power grids. On one hand, you have steady state simulations like PowerFlow, which is usually an approximation of the steady state that is used by planning and operation engineers to ensure that steady state voltages and currents are within some sort of limits. On the other end of the spectrum, you've got transient simulations, which really solve the ODEs corresponding to the power network. And this is used for like contingencies and any sort of disturbances to understand the transients happening there. Transient simulations are of course much more accurate than steady state simulations, but they take a lot of simulation time and especially haven't shown the scalability for something like showing like a realistic large system. So what we're trying to propose is something in between, where we have the scalability of a steady state simulations, but it avoids things like latent periods and transients, yet it can still approximate what the quasi-steady state of control actions are. So just some general issues with like the two big simulations today. Transient simulation, the main bottleneck is due to the large range of time constants in the power grid. So in the power network, if you see in the figure on the right, you can notice that that the power network really has a large time constant range. So if you take a look at just the electromechanical transient and the steady state, you can see the time constants range from like milliseconds all the way to hours. And this usually becomes a bottleneck in transient simulations as you usually have to respect the smallest time constant. So this requires you to have really small time steps, even though if I want to find the action due to something within the hours. And another problem is that you have latent periods where you have no real controls happening, and that causes unnecessary simulations. On the other hand, steady state simulations like PowerFlow really ignores the temporal dependencies that occur. So it ignores the order of events that control actions happen to finally reach that steady state. So with that in mind, we can kind of look at the power grid as a dynamic linear network with various injections. So for example, here we've got this two-bus system with a transmission line model in the middle. We've got a generator on the first bus and a load on the second bus. And when really, this is another way of looking at it, really you have in your generator, you've got P and Q current injection there. Behind these injections are various controls that ensure that the voltage is stable and so forth. But really you can look at it as like almost like a current injection. And what's interesting in this is that in this perspective is that now you have a Q and P injections from a generator. So if we consider the example of like a slow ramping up generator, the P injection actually has a slow ramp up in terms of minutes, whereas the Q injection is reacting with an automatic voltage regulation in the matter of seconds. So you can really see that they have different time constants. And this gives us the inspiration for actually defining our quasi-steady state. So you can write out the ODEs corresponding to the power grid as of, with a X representing like the voltage at each bus. And then we have some nonlinear equations, and it really responds to two sort of controls. You can really define it as fast controls and slow controls. We'll talk later about how do we actually define those. But you can see that with these fast and slow controls, let's assume some sort of window in which we assume the fast controls have reached steady state and the slow controls are stationary. So if we can assume this sort of time period, then we can put this back within our quasi-steady state, and we can show that we're really solving a set of nonlinear problems in which we have this time splice in which all our fast control actions like AVR in the last figure have reached their steady state, whereas things like slow generator ramping up are stationary, so they're just at a certain time point. So now we have got a set of nonlinear equations representing essentially our quasi-steady state. And the question is, how do we solve this? Power flow is actually a very powerful tool that is able to solve these nonlinear equations. And more importantly, governor-based power flow includes things like a frequency deviation to model these frequency responses to better model the quasi-steady state. So we're going to use a governor-based power flow as actually to solve for a quasi-steady state for a specific time window. And we can see here that this is an example of a quasi-steady state solver, sugar, as we call it. It's a tool that we've developed at Carnegie Mellon that's able to actually find what the electrical torque of an induction motor is after some sort of disturbance. And it's able to do this quite accurately. So now the question is, how do I define something that is a slow and fast time constants? And how do I define which one's a slow control and a fast control? So this definition is actually going to be user defined with obviously some minimum bounds. So for example, we have this tau max, which I can define arbitrarily. With anything less than that, such as AVR and primary frequency response, I can consider as fast acting. So in my quasi-steady state assumption, I'll assume that they've reached their steady state immediately. Whereas anything slower, like generator ramping or AGC, I would consider as stationary according to our quasi-steady state assumption. So now that we have this idea of which ones we can consider fast and slow, let's see if this is actually a valid assumption. So we do this by actually doing some experiments. So here we've actually tried to compare this against a dynamic simulation tool. And we used our sugar solver, which is a governor-based power flow, to compare against a dynamic simulation on this 39 bus system, in which we have a transmission line tripping followed by a load increase. And what we notice is the curves are actually defined by the dynamic state estimation, the dynamic simulator, and the markers are actually the quasi-steady state from sugar. And we notice is that it can very easily actually accurately find what the frequency and voltages are before and after the disturbances. So this helps us validate that this quasi-steady state assumption is accurate. Now that we have this quasi-steady state assumption, the question now is, how do I actually progress through simulation time? Traditional state transient analysis would actually use time steps, but we've actually defined instead an event. An event in our definition is anything that is an abrupt change in our quasi-steady state assumption. So for example, any discrete change in our network or an impulse change in our slow control assumptions will be defined as an event. And now we're able to actually progress through time in events rather than time steps. And what this allows us to do is it allows us to avoid things like transients, avoid latent periods, and it exploits the temporal sparsity that's present in the power network. But unlike just regular power flow, it actually considers the temporal dependencies of the order of actions that are happening. So in this example here, we've got this system in which we have an initial disturbance at T1, then we get our primary control response at T2. At T3, our secondary control response starts, and then before it's able to actually, our secondary frequency response is able to get it to frequency deviation of 0, and a disturbance happens at T4, and we repeat the process. So as you can see, we don't have an exact time step, but rather we're looking at the events that actually occur. And so there are different types of events that we can consider. We can consider like automatic generation control or any generator ramping, starting or ending, as they are. Those are impulse changes to our quasi-steady state behavior. Then there's things like network changes, so like transmission line tripping, transformer tap change, or load change can be considered as other types of events. And in doing so, what we have to ensure is that we have to ensure that events are always in order. So there are cases where we may have skipped an event, which would violate the assumption that these events actually do occur in order. And this happens as an example of if we start off with a generator ramping up and a generator eventually stops ramping, and we notice a transmission line has tripped. So we need to actually go back in time to actually find when that transmission line has tripped in order to actually uphold the order of events that actually occurred. So the way this entire algorithm works is we first build what's known as an event queue. And this is just a queue with prioritized based on when the event will occur. And we insert things like scheduled events such as like redispatches that we know will happen every 5 or 10 minutes. And Sugar, which is our governor power flows framework, initially starts with a quasi-steady state at the first time step, then progresses through each event and solves the quasi-steady state at each event. We're able to identify if the system is infeasible or not using an infeasibility analysis. And we've shown that Sugar is a robust enough framework to include this infeasibility analysis for systems as large as 80,000 buses. And what we notice is if another event has taken place during that same event, we go back in time by essentially doing a binary search to actually try and find that event. And this is the backtracking algorithm that we do to ensure that we can have this same order of events. So now let's look at actually how to simulate a larger system. So let's take this 8,000 bus system that we've shown. And we notice we first have a load increase, which causes our frequency to drop and have a primary frequency response enacted. Then we get a secondary frequency response to bring back our frequency deviation. Another at around time 60 seconds, and we have another load increase. And what you would think here is we would have another primary response followed by a secondary frequency response control actions. But what we notice in the middle of it is that a branch has tripped due to the generator ramping. And we did this using our backtracking algorithm. So after the branch is tripped, we eventually use the frequency responses to reach a steady state. And this is around 160 seconds. And then around 240 seconds, we have another load increase. And what you notice is we're able to avoid this long time period because of this event-driven framework, and we're able to avoid this latent period where nothing actually happens. So this framework is also scalable to much larger systems. We've taken this to test cases up to 80,000 bus systems representing the U.S. Eastern interconnection, and we're able to simulate, around this was 20-minute time windows in which we were simulating up to 80,000 buses system, and we did that in roughly 15 minutes. So we're able to show that because such a robust and scalable framework, we're able to solve extremely large cases that would be very useful for planning and operational engineers. So in conclusion, we've introduced this event-driven approach, which exploits the temporal sparsity of naturally in the grid to provide fewer simulations. And we did this by actually using a quasi-steady state approximation in which we used our Sugar governor power flow framework that's scalable to such large cases like the US Eastern interconnection. Thank you very much. I'll take any questions now.
Thank you, Julio. Paolo, please, for some reason, I cannot see if the question and answer panel, I don't know. I see the screen by Julio, but anyway, Julio, are you able to see the question, if there are any questions?
Are you talking to me, Professor, or to
Sorry. I was,
Oh, sorry. Yes, I don't see any questions there right now.
Okay, so I have
Sorry, I just got one question. Dan Molzan asked me if thank you for the interesting talk. Can you please compare your approach to singular perturbation ideas?
Mhm.
I'm not very familiar with singular perturbation ideas. If you could clarify that, I'd love to answer that.
Okay, it seems that you are including in your model, in equation 7 to 9, you are including active power limits, but what about reactive power and excitation voltage limit when modeling ADRs?
Yeah, so those are all implicitly defined. We have done a lot of work within the sugar framework to include continuous models for active, reactive, and AGC limits, all as part of within our governor power flow framework.
Okay, so could you be able also to model the influence of power converters of wind energy conversion systems on the overall system dynamics?
Yes, I think that's the future work that we're trying to do, is try to incorporate more control actions such as like the inverter dynamics, and then and one way we're going to do that is we're going to reduce the time constant so that it can actually capture those dynamics much more accurately.
Okay. Any other question? Can you see any other question?
I don't see any other questions right now.
Okay. So thank you so much. Let's move to the fifth.
I'm sorry. I think I did get another question from Julio. He says, thank you for the presentation. Could you please comment on computational aspects, computing time and convergence? So computing time, as I've shown, is we've actually sped it up a lot more after publishing the paper. And the reason we're able to do this is because we use a Newton technique to solve each governor power flow. And we've developed homotopy methods to actually go from one event to another very smoothly. So we can do that in very few iterations. And as for convergence, the sugar framework includes an infeasibility analysis, even for something like as large as 80,000 bus systems, where we can actually have guaranteed convergence, and any infeasibility can be identified. Any network infeasibility can be identified.
Okay, thank you.